This is checkpoint 3.12. They want us to find the unit normal vector for the vector valued function rt is equal to t squared minus 3t in the I direction and 4t plus 1 in a j direction. After we do that, they want us to find the unit normal vector when t is equal to 2. Let's begin by recalling some formulas. To get to the normal vector, we need a unit tangent vector, and the unit tangent vector will be given by taking the derivative of our position function and dividing by its magnitude. So the derivative of the position function is the tangent vector, but to make it into a unit vector, we have to make sure we normalize it. Now to get our normal vector, we're going to simply take the derivative of the unit tangent vector. And again, that might not be a unit vector, so we'll divide once again by its magnitude. Okay, let's start by finding the derivative of the position vector. And this time I'll write it with a slightly different notation. We have a 2t minus 3, comma, and just a constant 4 for the y value. And then we need to take the magnitude of this. That is going to be the square root of the first component, 2t minus 3 quantity squared, and then we add 4 squared. Okay, now that we have that, let us begin by finding our unit tangent vector. This is simply the vector 2t minus 3 comma 4 divided by the magnitude, which is the square root of, let's multiply this out. If I multiply this out, this is going to be using FOIL, 4t squared minus 2 times 3 is 6 times 2 is 12. The middle term is going to be 12t, and then plus 9. But instead of adding 9 to this, we need to add an extra 16. So 9 plus 16 is 25, and that will be our constant. Our next step will be taking the derivative of this, and to make it a little bit more manageable, I will rewrite the denominator as 4t squared minus 12t plus 25 raised to the negative 1/2 power, and multiply it by the vector 2t minus 3 comma 4, which now looks like a scalar multiplication. And with a scalar multiplication, if I want the derivative, all I have to do is take the product rule. Applying the product rule, we take the derivative of the first, that's a negative 1/2 times the inside, and the inside is going to be 4t squared minus 12t plus 25, and then raised to the negative 3/2 power, times the derivative of the inside using the chain rule. We have 8t minus 12, and so that's the derivative first multiplied by the second item, which is the vector 2t minus 3 comma 4. I'll continue on with the product rule. We need to write down just the first term, 4t squared minus 12t plus 25. This is raised to the negative 1/2 power. Now we take the derivative of the second term, which is just going to be 2 comma 0. Okay. As I look at this, I'm only going to be concerned about adding the first component, the x component, and we're going to, the second component is just going to be whatever is going to be left here on the first part. Let's do some simplifying if we can. I think I see a 2 here, And if we factor out a 2 that we can cancel, we have 4t minus 6. And we have this thing is a negative, and this is in a denominator. And if that's in a denominator, we're going to want to multiply this by, to match with the denominator, multiply this by, that would be 4t squared minus 12t plus 25. 4t squared minus 12t plus 25. Top and bottom, multiplying by 1, and that would give us a denominator of this thing raised to the negative 3/2 power. So let's continue on. This has a -1, so let's keep that negative sign there. And our denominator here would be 4t squared minus 12t plus 25 to the 3/2 power, positive now because I brought it down in the denominator. And then we have 4t minus 6. Now this thing is going to have a negative in front of it, so why don't we go ahead and distribute that negative sign. Oh, we can do it later when we start combining things. So we have a 2t minus 3 and a 4 over here. And then now this one is just going to have this component times 2, and we multiplied everything out with the common denominator. So my common denominator would be 4t squared minus 12t plus 25 to the positive 3/2 power, and then I would have a 4t squared minus 12t plus 25, and then this is going to get multiplied by 2 and 0. Okay, now let's just focus. Well, what I'm going to try to do here is I'm going to identify that my denominator is the same, and I can take that out. So let me factor that out, as in 1 divided by 4t squared minus 12t plus 25 to the 3/2 power. So I don't have to write that again. And then meanwhile, I will take my values, my other constants, and distribute it, and separate this into the x and y components now. Okay, so I'll put a negative sign out here and then multiply this out. So this will be a 4t times 2t, that's 8t squared. 4t times 4 is 16. Oops, 4t times 3, I'm multiplying it with this first. That would be negative 12, and then 6 times negative 2, that's negative 12 again, so that's going to be a negative 24t. That's our middle term, and our last term is going to be positive 18. And there's a negative sign, which I'm keeping out there for now, and then we'll add to that plus this thing, which is 2 times 4t squared minus 12t plus 25. Okay, so that's the whole first term, and then the whole second term would be 0 plus, and there's a negative sign here, so it's negative, and this one I can distribute. 4 times 4 is 16 t, and 4 times 6 is 24, and that negative, because of the negative sign being distributed, will become a positive. Okay, that's what we have so far. And then we will simplify this. Let's take a look at see if there are some like terms. If we multiply this, we'll distribute the negative. It's going to be negative 8t squared plus 2t. I think that should have been a 24. 24t, and then the plus becomes a minus, minus 18, and then we have a plus 8t squared, and here we have a 12t, times 2, and so that's going to be a negative 24t, and then an 18, negative 18, well, that's already there. 2 times 25 is 50. Okay, that is our whole first term, and let's rewrite our constant out here, 4t squared minus 12t plus 25 to the 3/2 power, and then let's see what happened with the simplification. We got these two terms are like terms and opposite signs. We have another set of like terms and opposite signs, so it's just a 50 minus 18. And 50 minus 18, I believe, is 432, which is a constant, and then we have a negative 16t plus 24. All right, I think that's it. That is our normal vector. We can factor out, looks like we might be able to factor out an 8 if we wanted to, and have it sitting up on top here. Oh, wait a minute, this isn't quite it yet. This is just the derivative of the tangent vector, and let us factor out that 8 that we were just talking about, so we can have the vector as simple as possible. We have 8 divided by 4t squared minus 12t plus 25 raised to the 3/2 power. And then now our vector, after we factor out an 8, will give us a 4 in the first component. And an 8 out of there is negative 2t, and an 8 out of there is 3. Okay. Now I wanted the vector as simple as possible because we still need to take the magnitude of this t prime vector that we just found, which is not that easy to do, but it turns out that the magnitude of a scalar times a vector is simply going to be the absolute value of the scalar, which is going to be positive anyway, so we can leave or get rid of the absolute value sign. But it's going to be 8 divided by 4t squared minus 12t plus 25 raised to the 3/2 power. And the magnitude of this one. So that one is going to be 16 square root of 16 plus negative 2t plus 3 quantity squared. Now, if that looks familiar, it turns out that if you FOIL this out, you're going to get this to equal to 8 divided by 4t squared minus 12t plus 25. We're going to raise that to the 3/2 power. And now this thing is raised to the 1/2 power, but if you FOIL it all out, this is exactly going to be 4t squared minus 12t, and then 9 plus 16 is 25. So this is a square root, which is raised to the 1/2 power, and half of that disappears. And then, well, instead of canceling this out, I'm just going to leave it like this, because what we're going to do is we're going to write your normal vector is equal to the derivative of t divided by the magnitude derivative of t. And without having to write this over each other, if these two were in a fraction together, I can see that these would cancel, and then I would have the vector divided by this expression. And that looks very similar, doesn't it? And so by canceling out the scalar, or the 8 divided by that something to the 3/2 power, I will have 4 comma minus 2t plus 3 as a vector divided by this thing, which is square root of 4t squared minus 12t plus 25. Okay, it's raised to the 1/2 power, but I put it under square root. And so this is it. This is your normal vector as a function of t. Then, according to the instructions, they want us to find it when t is equal to 2. So we'll simply put that in. Your n vector evaluated at 2 is going to be 4 comma minus 2 times 2 plus 3 divided by 4 2 squared minus 12 times 2 plus 25, all under square root. So what do we have here? Let's take care of the square root first. This is 4 times 4 is 16. 2 times 12 is 24, plus 25 is 1. 16 plus 1 is 17. So that's square root of 17 as your scalar that you're going to multiply the vector for, comma, and then this is going to be negative 4 plus 3 is negative 1. Okay, just to check, let us, since we're here anyways, let us take a look at our t, which is a fairly simple function, and let's put 2 in there. T of 2 will equal to, now we had that vector. The vector that we had was 2t minus 3 comma 4. So that's 2t minus 3 comma 4 divided by that same thing that we had. So instead of writing it over again, I will just put 17 because we know what that is. And this will become 1 over square root of 17 times the vector. This is 4 minus 3 is positive 1 comma 4. And just to check, if you were to take the dot product of these two vectors, well, first of all, they are unit vectors, and now you take the dot product of these two vectors, you're going to get 0, which is to say that they are in fact perpendicular. Okay, whew. I hope that helps. And there's a lot of tedious computation here, but if you just follow the steps, you'll be okay. Okay, good luck.